So let's discuss more about teleportation, and so we can generalize that to qubit teleportation. We talked about how to send a qubit. You can send a qubit also. So the idea is same, or you can use a group, or there are many versions to this. Okay. So what we do is we have a vector, okay, in TD. This is what a qubit is. TD. We were so Alice and Bob, they share. I mean, we have all HA isomorphic to HB, isomorphic to CD. Okay. So Alice and Bob shares a Hilbert. I mean, they have a Alice uses this Hilbert space as her system. Bob uses this as her system, his system, and they share a entangled pair between them, prepared long ago. So then she wants to send another one, which is HA prime, which is also isomorphic to this. A qubit is called qubit, d-dimensional, so it's qubit. Qubit of in this vector space she wants to send. Okay, so it's more or less the same, except we need to use this operator instead of we used Pauli matrices. Here we use the Weyl operators, generalized Weyl operators, generalized Bell state or Pauli matrices and all that. So we have this. This is equal to 1 by square root d summation I tens R I. Okay, this is in A, this is in B. Okay, in HA tens R HB. So Alice and Bob shares this. Alice and Bob shares this state. Okay. Now you have a chi which is in HA prime, which is isomorphic to CD. Right here. Now the system. So now system is in this state. Chi tensor this. Okay. HA prime tensor HA, or you can write it as HA prime. You can write it like that. It's in this Hilbert space. Okay. Now let's use, so the idea is same. You make a measurement. Alice has these two Hilbert space in her system. So she make a measurement, and then she gets a qubit. Sorry, she gets a classical vector, okay, which is in just a diagonal matrix like that. She sends us information, and he uses that information to get it back. So that is the idea. I mean, sorry, she gets what do you call it, dit or something? I don't know. I mean, a binary state is called bit. Yeah, this is a state which is in D possibilities are there in the whatever the. I mean, you can actually take it to be some 2 power n. That will be like n qubit. That will be n qubit. So it will be n bit. Okay. So we take it CD is a general thing. Okay? So so she sends. I mean, there will be two dits. Okay? She will have it. I mean, she sent 2 bits. Now she will send 2 dits, whatever. Okay? So we have this Weyl operators, okay, where Z and X is in between 0 to D minus 1. Okay? We have defined these operators. We have so this is these operators. This, I mean, which acting on any k is going to be x plus k plus x, okay, and e power. I mean, if you act just z, it will be just e power ikx. But since you have first applied this, you need k plus x. Okay? 2 pi I k plus x times z divided by d. Okay? This is the Weyl operator. E power I 2 pi I k plus x z by, here you have z by d. These are their numbers, okay, times k plus x. This is because you first act this corresponding w0x, and then you are acting. That's why you k plus x. Otherwise, this action is just e power I x z. Okay, so this is what you have. Now we have already seen that zx tensor 1 P. This is a prime E. A P A prime E is again the same this kind of vectors, except you will have A prime and A here. Okay? So this vector, so this in H A prime A is an orthonormal. So this is Zx varies in 0 up to d minus 1 is an orthonormal basis. This Y and B for this H A prime A. Okay, H A prime tensor H A. For that space, this is an orthonormal basis. So in particular, summation E. So I lighted A prime A also here. Pxy, x in the top or bottom, we have written. I mean, you call this as this. I am calling it as P. Shall I put it in the bottom? Zx. P Zx is this. Okay? We call it Zx. So P Zx in A prime A, Zx A prime A, okay, equal to 1. So this projection, this forms a positive operator valued measurement. This gives a positive operator valued measurement. So Alice measures this state. Okay. So you call it as P measurement, you call it as Pxz, Zx. Measurement in this. For measurement, you have to, I mean, you are just measuring for the first two qubits. Okay. First two qubits in this basis. Okay. So that's called, you have to prescribe the set of projection. These are this projection. P is X. Yields, what is the spelling? Which gives us, I mean, whatever. Measurement in this yields. This is yield spelling, right? I forget. I or E? I, okay. No, it doesn't look nice. We stop writing all these things. Okay, I think this is right. Anyway, it yields, it's clear. So, okay, measurement in this yields what? So it yields with probability, it yields some, I mean, yields this number. Okay. I mean, these are number, two numbers, okay, which is a value in Zn 0 up to n minus 1, 2. Okay. 2. This value with probability, with equal probability 1 by d square. And the state will collapse to, once you get one of those things, to collapse to, and if the result is, if, I mean, state will collapse to, we have to hit it by this projection. Okay. I mean, the probability will be trace of that, and it will be trace of, I mean, you have to take this vector and then hit this vector, and you have to take the trace, that will be 1 by d square, that will be clear, I mean, when you do the calculation. And you will get a operator, divide that operator by the trace of that will be the state. Okay, if you have something, it will collapse to this P Zx original whatever original state compressed by this projection divided by the trace of that. Okay, that will be the new state. So let us compute this. Okay. P Zx acting on that, whatever, acting on this chi tensor this AB. That will be equal to, we have a, so, okay. So what is this P Zx, this vector? This is W Zx tensor 1 acting on summation II, whatever, okay, Kk, Kk or II. Let's say L, I, K, what? K will be coming there. So let's take Kk, okay, Kk, K tensor K. divided by 1 by square root. Okay, so this, if you act on that, you will get summation, so 1 by square root d. There are other ways of doing, but let us calculate it once, and I will generalize to the group next, and there it will be different. Okay. This itself can be directly generalized. For example, instead of taking WZX, we have already done that. You can take a group. You can take this CD as you, I mean, I will write it. For instance, you can take a G, okay, mod G equal to that D. Okay, mod G equal to, yeah, mod G is D. Then you take an abelian group of G, then you take G hat, G hat. G hat is also abelian, I mean, G hat is a character function, which is one-dimensional, and it's also abelian, and that will also have D. Okay. Then you can define W alpha A. Okay. WA will shift, alpha will multiply by that. You have already defined all. You can use the whole thing. I mean, you can take L2G as the Hilbert space H, and you can do the whole thing. I mean, instead of whatever we have here, you will get alpha here. This is precisely the alpha, and it will shift like the whole thing will go through the same way. Okay? You can take it that way. 1 by square root d. So we are calculating this. Phi, what is phi zx? Phi zx is going to be, this is going to act only on this. That will become k plus x. Okay, and summation e power 2 pi I k plus x times z divided by d. Okay, times a. Okay, this is what the vector is. Okay, we are making the measurement in this vector. So if you want to make the measurement, we have to, after measurement, if the value, whatever the value we get is zx, okay, zx, then this, I mean, whatever the state will collapse, we have to divide it by the trace. We'll come to that. We have to hit it by the projection. That is just E zx. Okay. We have to hit that vector. P zx tensor 1. This 1 is in HP. Okay. Inner product with that chi tensor P. This is in EP. Okay. This is what we will get. Okay. Now let us just calculate it. So this is going to be, here there is a summation, here there is a summation. Okay. There are another thing, we have to write the chi also. This chi will look like summation CL some L. L equal to 0 to D minus. Okay. That is, I mean, this is just a decomposition with respect to the orthogonal vector. I mean, the standard basis. So this is going to be, here we will get a summation, which you call it as A. Here you will get a summation, which I call it as L. Here you will have a summation, which I call it as K prime. Okay. So this is going to be, so this vector, we are having the bra vector, not ket vector. So this is going to be K, as here I'm using K, no? So this will be K tensor K. Okay. And tensor, I mean, here there is nothing. Here it's 1. Acting on, this is W, the first one is W ZX, tensor 1. Okay. Or we can just directly write that. We have already know what we have already calculated. So this is just going to be K plus X. Okay. E power, there is something, E power. But since we are having the bra vector here, it will be the bar here. The constant will be the bar here. So e power minus I, e power 2 pi I, k plus x times z divided by b, okay, and d, and there will be a 1 by d something. So there will be 1 by d or 1 by d square. I think there's 1 by d square finally. I mean, we'll come to that. There will be a d coming from here. There will be a d coming from here. So that is just 1 by d only will get, right? 1 by d square. I think it's only, there is a 1 by square root d, and there is another 1 by square root d coming from this. This phi is also, there is a 1 by square root d here. I'm supposed to get d square somewhere. Let's see. 1 by d only we are getting, no, till now. We are getting a 1 by d, 1 by square root d, 1 by square root d. So there's a 1 by d. Okay. Then k plus x tensor k tensor 1. Okay. Then the other vector is chi tensor. Chi we can write it as, I write the CL also here. So I get only L here. Tensor k prime tensor k prime. Okay. This phi I have written here, k tensor k prime, and d is gone there. This chi I have written L and put a CL here. The sum is here. And this I have written here. Which one? These are all, this is the vector, this is the inner product I'm taking it. This will be a bra vector, right? You are right. Yeah, this is bra vector. That's what I said when I wrote it second time. I wrote it. Yeah, right. Okay. Now this vector will take an inner product with this. So k should be equal to k prime. So this k prime will become k. This will be 1, and this will become k. Okay. Now this k plus x should be L. So L will become k plus x. Okay. So this whole thing will be, there's a summation over only k. Okay. Then C k plus x. I replace L by k plus x, and e power 2 pi I k plus x divided by d. Okay. And there is z here. And this k plus x, this will go, and we will only get k. Okay. Okay. Now we replace, I mean, this is, so here, the sum is modulo d, ZD summation, modulo d. So if you replace k by k plus x, we can replace k by k plus x. We can make the substitution. So this will be summation over, again, let me call it k itself, k, c k e power minus 2 pi I k, okay, z by d. Then here it will be k minus x. Okay. This whole thing is equal to summation. This is what disturbing me. I should get 1 by d square or 1 by d. We are getting 2 entries. It should be, see, we have d square vectors. No, we are using d square vectors. Okay. So each one we should get equal probability 1 by d square. So we should get 1 by d square. So where is the other d coming from? We will get 1 by square root d from here. There are d square of this, but we will get 1 by d square from here, 1 by square root d, 1 by d will get. Where am I getting d square? We should get d square. This action is correct. This is 1 by square root d, 1 by okay. See, the thing is, these are the vectors. If you take the state, you will get d square, 1 by d square. Okay. I mean, these are vectors. What you get is a vector. What you have to consider is the state, actually. You have to take the state of this, state of that, and then take the trace. that will give you 1 by d square. So 1 by d you are getting here, that's okay. But actually the see, if you have this vector alpha 0 plus beta 1, okay, the probability of getting this is mod alpha square. Probability of getting this is mod beta square. So I think you should get, if you get 1 by d is I mean, this is the vector you are getting, each vector, but the probability will be trace of the corresponding states. We are only taking the inner product of the vectors. So if you take the state, it will be 1 by d square. Okay? So this is just the, I mean, we are calculating the state only, but we are calculating the vector, and the state will be this vector state given, I mean, state, pure state given by this vector. Okay, then you will get 1 by d square. Okay. Okay, now we have got this answer. Okay, so this is nothing but summation. So you can apply, so that will be applying W ZX star. I mean, applying WZ first. If you apply WZ, you get this. Okay, and then minus of this. Okay, that is what is WZX bar. Okay, right. So there is no plus here. Okay, so because you are applying WZ first and then WX first. Okay, WZX star of whatever that. So this will be summation CK. You can take summation CK. Whatever. K, but this is in B. See, what we are getting is we get those scalars, but the vectors, this vector, these are all B vectors. Okay, the vectors are in B, but we get the same scalars somehow. Okay, so this will finally we get the same vector in B. Okay, so what we get is W ZX. I mean, we get 1 by d whatever W ZX acting on this chi B. The chi is a vector in A only, A prime only, but with the same scalar, same vector. You can talk about it in B also. The same, they are isomorphic. So that is this vector. So you got that QD here. Now Bob will, I mean, this is with probability. This, I mean, this is not the state. You have to divide it by the, I mean, the collapsed state is, you have to divide it by the trace. This is we will get this state with probability 1 by d square. And the collapsed state is this. Collapsed state is W ZX. This. Now Bob applies. Sorry, star W ZX. I mean, Alice will get the measurement ZX. She will send that measurement through classical channel, and then Bob will apply that. So once Bob knows this ZX through classical channel, Bob will apply this on his vector. Whatever, he doesn't know the vector. Bob applies WZ to get this. This is what. So this is an example of what we discussed as LOCC channel, local operation classical communication channel. So the operations are local. The communication is through classical means, whatever. So this is an example of that. We can write that as follows. So we have a row in MDC. Okay. I mean, this is what we are doing. We have a row in MDC. We append this. Let's not worry about that. We append. So let's make some definition. Okay. I first have MD. I want to make an operation on MD tensor MD. I mean, this is HA. I mean, this is what Alice has. See, in the LOCC channel, one-way LOCC channel, which we define, if it is from Alice to Bob, okay, this is from Alice to Bob. Alice is making the communication. So Alice will do measurement. There will be our measurement is more generally what is called quantum instrument. Quantum instrument is just the collection of these kind of completely positive map, such that summation MX is a channel. For each mx is a completely positive map, which doesn't increase the trace. Okay, so such that this will be a channel. Okay, so usually a measurement is you will have operators mx which sum to 1 and that's one. On the other hand, Bob will apply directly channel. Here, Bob is applying unitary channel to do that. Okay, so these are all the channels involved. First, you take a row, and I mean row is in. I mean this actually we do that MDC, and then we get row times P. This will be in MD, tensor MD, tensor MD. Okay. And then we do this Phi XY, whatever we defined as Phi XY, Phi XY, Phi XY. We make this measurement. We measure with respect to this. Okay, that will take us to CD, tensor CD, okay, tensor M. Okay. I mean, this is the classical channel which I used C2 in the last class. It is CD here. This is just the diagonal matrices. Okay. CD, it will take us to this. And from here, if you have Z, X, tensor, something, rho, okay, then you apply, this will go to W of ZX, rho, W of ZX, star. I mean, here I apply only WX, but if it is a mixed state, you have to apply this. Okay, this is this one. So this will be in MDC. So you started from MDC, you have got back to MDC. And the final, if it is rho A, you should get the same state here. Okay, that's what. So I mean, you name different them, call it E, C, whatever. Okay. I mean, usually what they will do is call it as some X, tensor X. Actually, there is another communication. Classical, there is nothing, it's just identity map. This is XX is the Alice classical space. That without any noise, they can send it to some Y tensor Y. I don't want to write this all same thing. There is really no point in doing all that. Okay. So she will send this XZ to XZ itself, ZX to ZX itself. Okay. So this is just classical. You have all those communication, but what the final product, final map is just this. If you take a row, it will go to, or if you have a sigma AB, sigma A prime AB, okay, that is in H, that is in L of HA prime, tensor HA, tensor HB. Okay. The map, the whole map is, to call it as tau, teleportation map, is you have sigma A prime AB, okay, of this sigma A prime AB is going to be, you take sigma A prime AB, okay, then you are going to take the measurement. Okay. Sorry. You are going to take the measurement. There is going to be phi ZX tensor 1. Okay. You are going to take the measurement and you are trying to take the trace over A prime A only. Okay. Then you are going to apply this. You are going to apply this 1 tensor W1 tensor 1. I mean, this is in A, this is in A, this is in A prime, this is in A, and here is ZX. In the top or bottom, ZX. This is what you are doing. ZX, and you are going to apply the other side also. W is it. Trace, this is partial trace with respect to A prime. You take a state, I mean, our state will be rho tensor that, I will come to that. You take a state in the big system. You apply the measurement in the first two part means you are applying this and trace A prime A. You can write trace, you can take this trace A prime A is just trace here tensor this, but this WZX acts on this. Okay, I mean, I have to write it. One second. Let me type. Sigma A prime AB. Okay, this is the state here. Then you have P A prime A tensor 1. I'm writing the same thing again and again. Okay, 1 tensor. Then you have 1 tensor W of Zx. This is in B. The same thing, star here. Okay. So you have 1 tensor W of Zx. Okay. And you have the trace A prime. Actually, this is outside that. I mean, trace A prime will give an operator on HB. This is outside that, which you can take it inside. I mean, you are actually using WZX prime outside that. That's what you are doing there. Okay, but you can take it inside because trace acts only on these two things, tensor 1, that is the trace. So you can take it inside. So this is the final, this is the channel. You take a sigma A prime in, this is how it acts. So when, so this is what is the tau of this is. Transportation channel is this. Okay. So when sigma A prime A B is equal to rho tensor phi. Phi is the standard maximally entangled state. Tau of this, I mean, okay, I just write it here. Okay, AB is equal to rho itself. So this is the statement, which we have verified for pure state. We can verify, I mean, we have verified the pure state. We can do the same thing for mixed state also. I will more or less, its proof is same. I will more or, I will write it. Okay, I will write it. So we will prove it for a general state. Okay. Okay, I want to apply the tau. Okay. So one more thing. This W is at 1 tensor that. This can go past this and you can take it here. Okay. So you will get it here. Okay. Okay. So let us just write it. What we have is the following. Raise A prime A. Okay. That phi xy is nothing but 1 tensor, W Zx tensor 1 tensor W Zx tensor 1, that's all. Okay. W Zx tensor 1. It's not much space. I need a, maybe I should have taken the whole board. Okay, now it should be okay. Okay, I want to calculate this rho tensor this. What I have written, there is something. I mean, I have written a vector. It should be a state. Okay, it should be this. You should rho tensor B A B. I want to show that it is actually equal to rho. Okay, it is equal to raise A prime A. Trace A prime A, which is trace A prime A tensor, usual trace. I mean, this is the partial trace. You can take it as usual scalar trace tensor 1 if you want, acting on phi, that phi xy is going to be W Zx tensor 1. That phi is going to be k prime. That's a summation. No, it's going to be summation. And I'll write it down. This is equal to summation. I'll get all the summation here. Let me write it and take it. W Zx tensor 1A tensor 1B, okay, acting on this vector A. I mean, this is a A prime. tensor A, A prime. Okay. That's right. So this is in A prime. This is in A tensor 1. Okay. This is one vector. And W ZX star tensor on A. Okay. Tensor 1. Okay. This is what is this is. Okay. I mean, this is not this. I mean, oh, sorry. There's something wrong. I'm sorry. You should have said that. We are taking measurement with respect to phi zx, right? Phi zx. The measurement is taken with respect to phi zx. I wrote it phi ab. Phi ab is this vector. W zx tensor 1 acting on that is phi zx phi a. We are taking measurement with respect to this vector. Okay. So that is what I will get here, and that's what I will return. That's what I will get here. That's what this is. This whole thing is P ZX P ZX. That's what I have written. This is what is whole thing. This whole thing. Okay. So phi ZX. That's what we are taking the measurement with. Okay. Then you have rho tensor whatever that. So rho tensor again L prime tensor L prime. The same thing. This is the phi vector. Okay, phi vector. But here I have this W ZX star W ZX star. I can write it here because I can take this W ZX past everything, right? This W ZX, this thing I can. These are all first two factors. You have something, so I can pass these things and take it there. Okay, that phi will be looking like this, so I can take it here. Okay, now here the sum is over K prime L prime. Okay, I have this row there. Okay, K prime L prime. Okay, now this K prime, which is in this, so and I have to take the trace of A prime. This trace of A prime A, if you want, you can consider this as trace of A prime A, the scalar trace of A prime A, tensor 1. Scalar prime trace of A prime A is a inner product on the matrices. Okay, so you are actually taking the inner product of this vector, whatever this the second this vector and this vector. You are taking an inner product of. I mean, here is identity. This identity will act on this K. This act on this. So you will hit the inner product of these two rank 1 vectors. That is that is 1. That is 0 if they are not equal. That is 1 if K equal to L and K prime equal to L prime. Otherwise, it is not. It's 0. Okay, so that is the only thing which will survive. So we will have K prime equal to K equal to L, K prime equal to. So we will have summation over only K prime. Okay, so this will be K prime. Okay, so this will be K prime, and okay. So what we have is the following: W ZX tensor and K prime. So we will have the K prime. So W ZX acting on K prime. Okay, this is the A prime component. Okay, the A component has gone. K prime. Okay, W ZX and W ZX star will come here. W ZX star. Okay, and then there is a inner product W ZX of this K prime ZX star. That's right, and you will have You have this vector, okay, this vector that has gone. There is a row somewhere, no? Row is here. Okay, row of this. Okay, trace of. Then there is a trace of A prime A trace of sorry, A prime. I have taken the trace of A. I've just used the trace of A, the middle one. Okay, I use the trace of A so that K becomes equal to L and K prime equal to L prime. Only middle trace I have used. Okay, then I have used the trace of A prime of this. Okay, row of this. This is a scalar. This is a scalar. Now I have to use the trace of this, the first entry, times the final entry. The final last entry is W Z star Z W star ZX. This there is no star. There is no star here. This is W ZX. ZX L. This L is K prime. No, this is just yeah, K prime times W ZX. Okay. Now if you look at the summation, this row is a state. These things forms an orthonormal basis of MDC. This thing, this WZX, this thing. Okay. I mean, sorry, you bring this WZX here. I mean, this is trace, no? So you can bring this WZX here because it's trace. Okay. So this thing, okay. This is just the trace inner product of this vector with this, right? This is just summation over K prime of this vector, trace inner product. Okay? This is trace A prime inner product of this vector WZX, this vector WZX. Maybe there's a star and other thing you should worry about. ZX star row, I mean K prime. Okay. W. Okay, this is the orthonormal basis. Sorry, I'm not using this as orthonormal basis. This is the orthonormal basis. This is not orthonormal basis. This is also orthonormal basis of that, but I use K prime. This orthonormal basis. WZX row WZX. Okay. This thing. Inner product of this with respect to trace. Trace A prime. Okay. Times W of ZX row W of ZX star. Now wait, sorry. Times what? Times K prime. Times K prime. I mean, time K prime. Then I apply this, sorry. Then I apply this W of ZX. Let me write this. Okay, this is what I have. I have summation K prime. This thing, trace inner product with this, okay, times K prime. So this is an orthonormal basis for the matrices. So I am taking inner product with this and sum over this. This is like the orthogonal Fourier expansion. So finally, I will get only this, right? Only this. So this is just W of ZX inside W of ZX star row W of ZX, W of ZX star, which is equal to, that's all. Okay. Here, I mean, it will be, I will use the same technique again in the group, more general group thing. It will be clear. Okay. So that's what we have done. Okay. Oh no. The camera was pointing there. Sorry. Okay, anyway, I am going to repeat the whole thing again. So for a general thing, that's what, but here what we have used is the trace inner product. See, what we have done is the following. We want to apply this tau on this. Okay, let me say, summarize it again. So this is the map, tau acting on this. Okay, the tau acting on this vector. So that vector is in the middle. It's here. Okay, I mean that vector. This is summation of this is whatever that phi is. Okay, that vector is in the middle. Then you have tau of this is you take, I mean, this is the phi vector. I mean, this is the phi xy state. This is the entangled state, phi xy state that you are taking the measurement with. Then you are applying the finally this wzx. So it is just the trace in using the trace inner product we get this. We use the same idea again here. Okay. Unfortunately, I didn't change the camera. I can't explain the whole thing again. Okay. This whole thing can be generalized with the group and its dual. I mean, its character group, but it's the same thing. It doesn't yield anything new. It just dimension is what matters. So here, suppose if you have a G is a finite group, you are not, we don't care whether it is abelian or not. It's just a finite group. Okay, and U from UG, G in G, contained in MDC, okay, is a unitary representation, irreducible unitary representation. I'm going to use the same idea here. So, okay, irreducible representation of G on CD. Okay. Then how to do this teleportation in this? Okay. So assume d square is less than this. Okay. First notice that summation UG rho UG star, this will be a scalar. Clear? That's because Schur's lemma. Schur's lemma says that if you have a irreducible representation, maybe a lemma, I'll just write it. If some t commutes with all those things, okay, TUG equal to UGT for all G, okay, then T is equal to lambda times identity. This is a version, I mean, this is not Schur's lemma. Schur's lemma is about intertwiners. This is something, a particular case of it. The proof will be clear. So it's UG is a irreducible representation. We have assumed UG is to be irreducible representation. So irreducible means it doesn't have any invariant subspace. Okay? So the only invariant subspace are either trivial 0 or the everything. Okay? Now notice that since this commutes, this relation, since it commutes, image of T, range of T and kernel of T are invariant subspaces. If kernel of T is everything, T is 0, so we don't care about that. So kernel of T should be 0. So kernel of T should be 0, and the image of T should be everything. Okay, the CD itself. Okay, because they are invariant subspace. That is clear, no? I mean, they are invariant. UG of T xi equal to T UG xi. Okay? If xi, I mean, anything in the range means it will look like this, T xi, and UG acting on that, it will be T UG, so it is again in the range. So, I mean, range is invariant under UG, and the kernel is suppose T xi equal to 0, then UG of T of UG xi is also UG of T xi, which is also 0. Okay, so for both kernel and images, it's clearly they are invariant under that. So kernel T should be 0 because it's non-trivial, and that should be this. So without loss of generality, we can assume T is self-adjoint because if G is a group, TUG equal to UGT. So T star, you can shift it. T star also commutes with this. So you can take T plus T star if you want. Okay? And we'll do the same thing. So without loss of generality, T is self-adjoint. So if it is self-adjoint, there is an eigenvalue for that. Okay, lambda is a lambda eigenvalue. Lambda eigenvalue means T minus lambda I is not invertible. But then T minus lambda I also commutes with this. Okay? T minus lambda I UG equal to UG T minus lambda I. Okay. That will imply that T minus lambda I kernel, I mean, it has a kernel. So kernel should be everything. So this should be equal to 0. T minus lambda I equal to 0. This implies T equal to lambda. Okay. Okay. So this is so if something commutes with everything, then that is 0. Okay. Now UG rho UG star 1 by G mod G, okay, commutes with everything. UG naught, this UG naught star equal to same thing, right? You can take it inside. It will be the same summation. It will just shift it. Okay, summation UG rho UG star, which is equal to UG naught G naught G G naught G, but that's the same thing. It's the same thing. So because of that, it commutes with this. So this implies this is equal to scalar. But that should have the same trace. So because of that, 1 by mod G summation UG rho UG star should be equal to trace of rho times identity divided by D. Okay. Identity divided by D has trace 1 and trace rho is that. So this whole thing will have trace. This will have trace rho. You can take UG star there. This will be trace rho. And you are dividing by, I mean, there are G in G. There are, you are dividing by this. So the whole thing will have trace 1. So this should also have trace 1. So this summation has to be equal to this. Okay. Okay. I don't know whether when we started I said this. Maybe I can orally give a proof of this. If you have Mn tensor mm, this is general thing. If you have x, one tensor t equal to one tensor t x. Okay? X is in Mn tensor mm. Okay? T is in mm. Then x looks like S tensor 1. I mean, it is just the commutant of Mn in this is this. Commutant of Mn tensor 1 is 1 tensor Mn. If some x in this commutes with all 1 tensor T, it should look like S tensor 1. That is just clear. You take any 1 tensor T. Okay, that is just going to be T. That's all. It commutes with any x. X you can consider as matrices of this size with operators xi. So now if you use that matrix relation, it will just each xij, this x will have xij with xij coming from this. So that will commute with all those, T will commute with all those things. And this is true for all T, this is for all T. Okay? So those xij has to be scalar. So if it is scalar entries with that, that is clearly in an Mn tensor 1. Okay, so the proof is clear. Okay. Of course, the commutant of all matrices, I mean, something commute with all matrices in that is scalar, you can directly, it will commute with all the partial, this kind of Eij, this Ij. If you use that, it commutes with that, you can prove that directly that it is a scalar vector. Okay. So from that, it follows that summation UG rho UG G in G 1 by G, okay, tensor 1 T. Okay. This is in MD, tensor MD. Okay. What is the statement? Mm. I mean, that will also be one. I want to use that. I have this is the statement. You take sigma, a state in this, okay, a state on that. Okay, then this UG tensor one. Okay, sigma UG tensor one. Okay. Then you take the summation 1 by mod G, whatever. Okay. Mod G this times G, this G in G. Okay. The sigma is the tensor. Okay. This is equal to, so 1 D of that, I mean, 1 in the first entry, D tensor, partial trace of this, trace of, you call it as A, this is B or whatever, AB, okay. Trace A of the sigma. Okay. So you get the B entry here. Okay. Now we should have the same trace, 1D by D maybe. Okay. Yeah. Because you take this will commute with all operators of this form, 1 tensor A, whatever. Okay. So it has to 1 tensor, B tensor 1. Because of this. I mean, it will commute with all those UG. So UG is irreducible. So it will commute with, I mean, UG is irreducible. Because of that, it will commute with all operators, or I mean, by the same Schutz lemma, whatever. So it will be of the form B tensor 1. So this is how it will look like. Okay. Okay. So in particular, you take this phi, the entangled state phi, the maximal entangled state phi, okay. UG tensor 1, okay. UG tensor 1, okay. Summation over G in G, and there is 1 square 1 by G mod G. Okay. This will be equal to 1D by D tensor. You take the partial trace with respect to the first entry, first factor. That will be 1D of the other one. I mean, this is that summation II. I mean, this maximal entangled vector. So that will be again 1D by D. So you get 1. I mean, the one MD tensor MD, okay, or 1 AB or whatever by D square. Okay. So from all these things, we get that UG tensor 1 P, the same thing, P, UG star tensor 1, okay, these things is equal to D square by G mod G equal to 1. Correct? That's summation over G. So this gives a POVM, positive operator valued measurement. Okay, that's all. That's for that only we have done all this. Okay, this gives a POVM. Okay. So now take, so now we have a CD. We have a vector in CD. Chi is a CD, vector in CD. Okay. This is what Alice has. I mean, this is HA prime equal to HA prime isomorphic to HA, isomorphic to H prime. And equal to these, all these things are CD. Okay. Okay. And you have a chi, a vector in HA prime. Okay. Now Alice wants to send this chi to this person, B. Okay. And Alice and Bob shares. Again, the same thing. Shares this vector. A summation. This is the T, AB. Okay. 1 by D, 1 by square root. Okay. They share this. So now she makes the measurement with respect to this. Okay. She makes the measurement with respect to this, and she gets a G. Out of this, she gets a G. I mean, this is summation G, no? Summation over G. So the value, classical value you get is a G. She sends that G. Then that person, Bob, applies this UG in his system. Get back to this. So that is the idea. Okay? We do the computation, which will be more or less the same idea, which I have used it. Okay. So Alice has the state chi. Okay? And that state is appended to this state, phi. Okay. And they make a measurement with respect to this POVM, whatever, using this G. So what we will get is summation G square by mod G. Okay. We are just D square by mod G, summation over G. Okay. Chi, what is that? UG tensor 1. UG tensor 1. Okay. P, it's this way, sorry. I mean, measurement means you have to take the inner product, right? You will have this P, this is between A prime A. Okay. A prime B, maximal entangled state. Okay. Tensor 1B, sorry, if on this, it acts as UG star tensor 1. Okay. This whole thing, tensor 1. Okay. Inside, you have the Alice vector chi tensor this phi, which is in BAB. Okay. That is what you have. Okay. And this is K prime. I mean, this is equal to D square by mod G summation over G K and K prime. Okay. This is, I mean, this is a vector. So it will be K tensor K prime, right? K prime. Sorry, K tensor K. K tensor K. Okay. Then you have the UG star acts on this. UG star acts on this. Okay. Tensor 1. Okay. And you have chi tensor K prime. Tensor K prime. The summation is over K and K prime. K and K prime. Okay. The summation over G, I mean, I have expanded this. I have expanded this as this. I have expanded this as this. Okay. And here it is K prime, K prime. Now this K and this K prime. In the middle one, there is nothing. I mean, middle one, only these two things are there. That's the same thing we used there. But instead, we use trace inner product. Here we are using the simpler thing, ordinary inner product. This K and K prime, they have to be equal. Okay. So this K prime will become K. Okay. And here we have K. So this will be D square by mod G. Okay. Summation over G. Summation over G. And what do you have? I have K. Okay. Summation. There is no summation over G. Sorry, there is no summation over G. One particular G. Sorry, there is no summation. I mean, the collapsed state only we are measuring. Collapsed state, there is no summation over G. Actually, there is a summation G in the earlier thing. That is because, I mean, that is just a notational thing. You just append it with the classical state and sum it over. Okay. That is to get back the row. That is why I summed in the last thing. So with that, keeping in that mind, I put the summation. I mean, that is to get back the row as it is. For that, to do that, you need the summation. If you go through that, it will be clear. Okay, maybe I'm getting confused. Okay, so there is no summation. There is only K. Okay. Now what you have is you have K here, and you have UG star what your UG star, and you have the chi here, okay? Chi here, and then you have the k here, which is nothing but d square by mod g. There will be a d somewhere. There will be two d's coming from there, no? Again, there is a d square. I should get 1 by mod g. Second time I'm getting this problem with d square. So you will get a square root of d here. You will get a square root of d here. That will cancel only one d. Why is it d square by? I need to cancel the other d also. Last time also I had the same problem. But why is it that this is such a scalar problem, but I'm missing something? I mean, you will get a 1 by square root d from this. You will get a 1 by square root d from here. So you will get, but I have to get this d square getting cancelled, because see, the point is there are g's, mod g such POVM, the operators in the POVM, or the number of operators is mod g. Each one has the same probability. So it will be 1 by mod g is what we are supposed to get. Okay. I think that, okay, again the same reasoning. We are only constructing the collapsed vector. So if you use that, you have to again divide it by, I mean, this will be 1 by, I mean, this, we are just taking the vector. We have to take the vector. So the d will go away. I mean, you will get a 1 by d here, you will get a 1 by d here. So that will not be there. So anyway, this scalar, you forget it. And we are only calculating this state. Okay. This will be 1 by g only, whatever. This will be some scalar. What you have is UG star chi. You take the inner product with k, and you will take in this vector k. So finally, I will get is UG star chi only. This is what you know. G is the value you get, some scalar times this. Okay, the collapsed state will be UG star chi. Okay. So the value Alice get is G. Alice sends that G, he applies that UG to get the chi. That's all. Same idea. It is just the same idea from 2 dimension everywhere, but we are just writing it in different way. You can do the same thing for a row also, what I have done. I mean, use the trace. No, that's a good exercise. What I have done for WXY, you can take a row here, and you have to apply this both conjugated, both add function you have to use, and you will get the same thing. But you have to use, instead of this inner product, you have to use the trace inner product, and you have to use the k prime, that partial isometry, which is an orthonormal basis for MD. So you have to use that, and you will get. So that's all about teleportation. Okay. I will just mention about what is called super dense coding. There's not much to it. So till now, what we did was Alice wants to send a quantum state. Okay. Till now, Alice wants to send a quantum state. So she did some measurement, and she got some value, classical value. She sent it by classical communication, and then Bob applies something. This super dense coding is a dual to that, dual version of that. She wants to send suppose if it is possible to send quantum state through communication. Suppose quantum communication is possible. There is quantum wires where you can send a quantum state without any noise. The state should, I mean, it shouldn't interact with the environment. It reaches there safely. Okay. Then by sending one quantum state, you can actually send 2 classical bits. That is what is super dense coding. They say it's something really very strong. But the other thing is you have to share a EPR pair before that, maximally entangled state. So here again, Alice in this state HA, Alice state, HB is Bob thing, okay? And they both share phi, BB. is the maximal entangled pair. The same thing by square root d k tensor k. Okay, summation. Okay, the same thing, they share it. Okay. Now she wants to send something. Okay, this is just a, I mean, this is qdit, but you can talk about qbit if you want. I mean, qbit is easy. Okay, so okay, let's forget about. Let's just write a qbit. Okay, suppose they have this. They share this 1 by square root 2 0 0 plus 1 1. Okay, this is the maximal entanglement. Okay, she has to send. There are 4 2 qubits. Okay, 0 0 0 1 1 0 1 1. Okay, suppose Alice wants to send 0 0. She does nothing. Alice has a qubit, Bob has a qubit. Those 2 qubits are in this state. So suppose Alice wants to send 0 0, she does nothing, just send her qubit. If Alice wants to send 0 1, she applies the Z matrix on that, which makes a minus Z on that, right? Yeah, I believe, yeah, Z matrix, Z on that. So Z to this her qubit, whatever she has a qubit, she applies, she can apply, she can do local operations, she can do. Z tensor 1, she applies and sends that qubit. Okay, I will orally say that's not much to say. If she wants to send this, she applies X and sends it. Okay, if she wants to send this, then ZX and sends this. Okay, then this, so once she applies, she doesn't do anything, it will be in this state. Okay, then Bob does I mean, if he wants, he can apply Hadamard state and then apply a usual measurement in this. Otherwise, he can make a measurement in this 4 qubits, right? This plus, I mean, this plus or minus, and then 1 by square root b 1 0 plus or minus 0 1. These 4 things forms a basis, right? Now Bob has 2 qubits. He can make a measurement in this 4 qubit. He will precisely get one of these things if he makes a measurement. Or he can apply Hadamard thing, this thing, 1 1 1 1 minus 1. He can apply that. Okay. Then he makes a measurement in this qubits, this 4 qubits. This, not the entangled one, just the usual classical bit. You will get the classical bit as it is. That's all. There is nothing to this superdense coding. That's all. Okay. They both share a qubit. I mean, initially, they know what the qubit is. The point is, these are all several values. I mean, using these bits, you can code a message or something. Okay. But those qubits are well known qubits. I mean, these qubits this is a sharing qubit. This entangled state is known. Okay, these are all arbitrary ones. There are 4 of them. 4 possibilities are there. So if she wants to send any one of that, she applies the corresponding gate here and then sends it. Okay, send her qubit. Alice has both a qubit. Sorry, Bob has both a qubit now. He applies Hadamard matrix and makes a measurement, and he will get the result. If she sends, if she wants to send this, she doesn't do anything. If we apply Hadamard matrix to this, for example, if you apply Hadamard matrix to this, you will get this value. If you apply Hadamard matrix to this minus of this, he will get this 0 1 value. If you apply Hadamard matrix to this, you will get the 1 0 value. If you have this minus this, you will get the 1 1 value. If you apply Hadamard matrix is okay, 1 by 2. Okay, that's what you get. So this is superdense coding. Applies the qubit, he applies Hadamard matrix and makes a measurement in this basis. He will get the classical qubit, whatever Alice wants to. That's all. So this is superdense coding. Okay, and you can do the same thing for WXY. The same idea. You take the entangled state summation. If she wants to send ZX, apply WZX and sends the qubit, and there he applies the d-dimensional Hadamard matrix is there. Or it doesn't matter. He can make a measurement. I mean, that's what it means. Making a measurement in this entangled basis, whatever that basis, the phi is ZY, ZX we said. In that basis, if you want to make a measurement, you have to apply Hadamard and then you get the 0. I mean, those qubit value. Okay? He will get that. That's all. This is superdense coding. I will stop here. Okay, we will stop the course. Course ends here. What happened? What did you press?